I'm Puwasala, and this talk is directly followed from Dilini's talk. So basically, I will go into the technical details of the proposed framework. I can skip this one because the time we have. And I would want to say that in this method, in this framework, we are actually utilizing the temporal correlation and the information that we gain from the nearby sensors. So this comes to the proposed framework. I have given the step-by-step framework in this picture. So basically, we want to first think what is the variable or the target variable that we want to detect anomalies in. Once we decide that, what we going to do is we want to build a model that can predict the typical behavior of our target variable. How we do that is we want to have a set of predictors to predict the typical behavior. So maybe suppose we have just data from one sensor, for example, in a downstream sensor. So then we can choose the predictors like other water quality variables that is measured in the same sensor location to predict our target variable. I'll take an example for target variable as nitrate or turbidity, and we can have predictors like conductivity, dissolved oxygen level, water temperature, such a set of variables to predict the typical behavior of our target variable. And the new thing that we are also introducing is, suppose we have a sensor that is upstream, which is flow connected, that is, they are sharing the same flow, and then we can actually get information from that upstream sensor to predict our target variable measured in the downstream sensor. However, if we are using the upstream data, then we have to be mindful of getting the correct lag time that corresponds to the time the water it took to flow from upstream to the downstream sensor. I'll talk about that in next few slides. So once we identify or clarify the target variable and the predictors, then we can build a model. So basically in this proposed framework, we are building a generalized additive model, which is having that capability to capture the nonlinear relationship between the variables. And then we are actually going to observe the residuals from that model. Whatever we cannot predict from that model will be left over in the residuals. So we are actually expecting these residuals to have a small, close to zero, and no any unpredicted patterns. But if we have those, then we want to detect them as our outliers or flag them as our outliers. So to flag them as outliers, we actually use data. We use the means of extreme value theory to come up with an outlier threshold. And then finally, we do some evaluation to see how well our proposed framework is working. So Dilini talked about the data here. So again, I'll briefly say we are using Pringle Creek data in Texas, USA, and data were retrieved from NEON database, and their sampling network, they placed two sensors about 200 meters apart. And both of these sites measure different water quality variables. So, but in this study, I'm only looking at the turbidity, conductivity, dissolved oxygen level, and temperature. The time that I'm considering is 2019 October to 2019 December, and the frequency is 5-minute intervals. Let's see some plots. So in this time plot, I am actually plotting, in each facet, I'm plotting different water quality variables, and these are colored by the upstream, colored by whether they are observed from the upstream or downstream. So basically the gray color is downstream and the orange color is upstream. What we can take from these plots is that all the variables having a close relationship between the upstream and downstream sensor, which actually give us some information that we could use upstream information to predict the downstream data. However, in this application, I'm just targeting the downstream turbidity. And these red points are the points that we are targeting to detect from our anomaly detection framework. By distinguishing with real water quality events, as Dilini explained. So basically, in a river system like this, when fresh water comes to the system, the turbidity will go high and gradually decrease. So that is a real water quality event, which we have to capture or model through from our given model, but that has to distinguish from our target technical anomalies. So to model that real water quality event, we can actually use the information from other water quality variables. So in this picture, I'm showing you the other water quality variables measured in the same sensor location. And if I go to the next slide, here it is showing you the other water quality variables measured in the upstream sensor. When we use upstream sensor, actually we are having this advantage of using the turbidity, the same target variable, but measured in the upstream location. So now we come to the modeling part. This is the main model. I'm modeling the downstream turbidity with generalized additive model. So these Gi and Hi are some smooth functions, and Zi are the predictors that we use. That is the other water quality variables that we use to gather the information, additional information. And also we can actually use the lagged responses or the past observation from the response variable. We also call it as autoregressive terms. So depending on different sets of predictors that we use, I am going to simplify these to this main model to 5 models. Remember, I'm modeling the downstream turbidity, but I can use different sets of predictors depending on the scenario we have. Suppose we have only one sensor location, then we can use other downstream variables that is measured in the same sensor location. And small integration to that model will be adding lagged responses. Suppose we have another sensor location in upstream to our target variable, then we can really use the lagged upstream variables to predict our downstream data, downstream turbidity. So the lag time estimation is very important. I'll come to that in next slide. Another small integration to that GAM up is adding lagged responses. And also we can use upstream lagged variables as well as other water quality variables measured in the downstream sensor to predict our downstream target variable, which is the turbidity. Okay, now let me talk about the lag time estimation. So lag time basically is the time that water takes to flow from upstream to the downstream sensor. And this time is, depending on this time, we need to calculate our upstream lagged predictors, which we use to model our downstream turbidity. However, we think that this lag time depends on the upstream river behavior. So to capture this information, we are using the methods of conditional cross correlations. I'm not going to go to the math behind that, but I'll explain in simple words what's happening here. So suppose we take the downstream turbidity and upstream turbidity, and we then calculate the cross correlation between upstream and downstream at different lags, at lag 1, lag 2, up to lag k. But we calculate this cross correlation conditioning on the upstream water level and upstream water temperature. Here we choose upstream water level and temperature because we think that that could predict what is happening, or that could observe what is happening in the upstream sensor. So we build some model to get these conditional cross correlation, and this comes, the conditional cross correlation is estimated for all the time points. Once we get that, we define the estimated time lag as the lag that gives the maximum cross correlation for a given time point. Okay, that's our definition, and that is how we use the data-driven approach to estimate this time delay. Let's see some plots or results. So in this plot, I'm showing you the estimated conditional cross correlation in the first panel, then the estimated time delay or time lag in the middle panel, and then we did some significant tests to see whether the estimated conditional cross correlations are significant or not. Once we get these time lags, we can then use that lag to compute the upstream lagged variable, which we can think of having the maximum, or observe to have the maximum cross correlation between the upstream and downstream sensors. Before doing that, I also wanted to see how the estimated time lag is behaving with the upstream predictors. So basically, in a river system, we expect that when water level in upstream goes high, the time the water to go downstream will be quickly. So that means the DT, or the lag time, will have a negative relationship between the level, which is actually showing with our estimated time delays. However, we are not sure about what is happening in this point, but it is having a high prediction interval, so we are not considering that. Yeah, temperature. Temperature is also becoming a significant variable in our models. However, we are not, at this moment, we are not sure why it is becoming significant. Maybe it's because of the seasonal effect between the variables. Yeah, that is about that. And then once we get sorted with our models, we then take the residuals and then use that residuals to detect an outliers, or come up with the outlier threshold. So to come up with that outlier threshold, we are using the extreme value theory. So I'm not explaining the math behind that, but basically what it is doing is it fit a model for the extreme values of the residuals and estimate an outlier threshold. These are the results. So in the first panel, I'm showing you the turbidity with the actual outliers pointed out in red, and below plots, I'm showing you the residuals for each of the model that I fit, and also color by the true positives, true negatives, false positives, and false negatives. Kat gave a good explanation of what are these true positive, true negatives, and so on. So I'm not going to go through defining what are they. However, if I see this plot, these black points are the period that I choose to calibrate my initial outlier threshold according to the extreme value theory algorithm that I'm using. After that, any point that is come to the system, or the residual streamy residuals, I can use that calibrated threshold to detect whether it has an outlier or a typical value. So the green points are the true positives, and the red points are the false negatives. So basically, in this type of settings, we are trying to minimize the number of false negatives. But we have to also take care of the false positives, because we don't want to blow up the false positives by minimizing the false negatives. Another takeaway from this plot is that the model that use just the downstream data, just the downstream other water quality variables, are poorly performing, in the sense they are missing a lot of true outliers in the data. Okay, I have done some evaluations. So basically, I have calculated the true positives, number of true positives, true negatives, false positives, false negatives. And depending on them, I have calculated this optimized precision. Optimized precision is a measure that we can use for to evaluate imbalanced data, and evaluate methods which uses imbalanced data. And we expect the optimized precision to be higher. So when optimized precision is higher, that indicates the method is performing well. According to the optimized precision, down AR method is performing well. However, we note that it is having a large number of false positives than any of the other methods, except for this method, this stray algorithm. Actually, this, I should say, the stray here is the method that uses odd-water, the methods developed in odd-water package, which use a feature-based approach that Delaney talked about. So for the comparison, I am using that method to see how well our method is doing. And also, I should say, the model that uses upstream data and downstream data are also performing quite well. It only misses one outlier, but it is actually having less number of false positives than the first method. However, the model that uses just the downstream data is performing really bad. So the takeaway message here is, if the practitioner is very critical about the outliers and they don't actually care how many false positives you identified, but I really want to detect all the false negatives, all the true outliers, then they can go with the GAM down AR model, and it uses data from the one sensor location. So if you are worried about the cost of having two or more sensors, then you can definitely go with GAM down AR model with the proposed framework. However, if someone is actually concerned about the operational cost that is involved in, if you identify any outlier and you have to send someone to inspect that and see whether it is an outlier or not, then they would like to have a balanced situation between the false positives and false negatives. In that case, they actually can use the GAM up down method or GAM up AR method. So that is the takeaway message. And that comes to the conclusion. So we have proposed a new framework to detect technical anomalies, and it involves utilizing information from the nearby sensors as well as temporal correlation between the variables. And also one thing I should say here is that if you are concerned about the cost that involves in having two sensors nearby, then we can maybe place low-cost sensors together. For example, if we want to detect anomalies in a nitrate sensor, which is an expensive sensor, and we cannot afford to have that expensive sensors nearby. But if we can have low-cost sensors that measure turbidity, conductivity, such type of other water quality variables, and they can actually predict the nitrate along with the other water quality variables observed in the same sensor location, then actually we can maybe think of implementing this method, which is actually giving us promising results. Yeah, that comes to the end of my presentation. And if you have any questions, I can, let's see, we can answer together, Delaney and me.